All right, today we are going to be looking at our recap video number 6, which covers kind of our last two big topics that we talked about in AP Calculus. One of them being slope fields with differential equations, and then the other one was the one just before that, which was areas and volumes for thinking about things in the plane, building things out of the plane, rotating things around an axis, etc., etc. I've put my face in this video because some kids in 2018 said they enjoyed seeing Mr. Lakin's face in the video, so, you know, I got to keep up with Lakin the best that I can. All right, so to get started, slope fields and differential equations. A slope field is a visual representation of a differential equation. Remember, a differential equation is something that has that dy, dx in it. Those are our differentials. So we're talking about a picture of slopes, which makes sense then that a slope field would be a picture of slopes, a field of slopes in its literal translation. So typical question in past AP free response has been to sketch on this type of thing. So we practiced, a slope of 0 would be some sort of horizontal line, a vertical slope or an undefined slope, right? When you divide by 0, it would be like that. And then in general, AP cares about the relative steepness of your line. So, this would be a slope maybe of about 1. And then you would draw steeper to represent a slope of 2. You would draw shallower to draw a slope of 1/2. And they're looking for just kind of the general flow. Those of you that were in my class, we talked about wind direction and kind of like following the flow of the current type thing and thinking about an electrical field. All of those are different ways that you can think about finding your slope field. So there were several years in a row where that was definitely a thing. It hasn't shown up as much, which means we're kind of thinking maybe it shows up in the multiple choice, but we don't have access to the multiple choice, so not really sure. So these relate then to solving your differential equation. Again, that differential equation, so you have the dy and the dx in there. So your first step is always to separate your variables. Then you want to take the antiderivative plus c, find c, and then solve for your particular solution. These are pretty standard on free response questions in terms of what you get your points for. And we'll kind of practice that as we go through some practice free response later in the video. Okay? All right then, area and volume was our other big topic that was towards the end of third quarter. So we're going to draw some pictures to help represent our different visuals of area and volume. So let's start with this concept of top minus bottom in your notes. Go ahead and give yourselves two functions. We're going to go with function g. We'll do g of x more particularly. And we will talk about function f. So if I wanted to find this area that is trapped between those two curves, well, area should be something with an integral. So the area that's in yellow will be equal to the integral from wherever these things are intersecting. We'll call this A and call this B. And then you want to think about a representative rectangle would draw from here to here, right? That would be a rectangle. And ideally, those rectangles are getting infinitesimally smaller, that dx concept, Riemann sums, etc. So thinking about these rectangles, my height is going to be this red curve minus this blue curve everywhere along that interval. So g of x minus f of x, and then I got to make sure that I close out with the width of each rectangle. Okay? This would be slicing perpendicular to the x-axis, which is why our widths here are dx's. It's a change in x representing the width of each rectangle. All right, next to that one then, we're going to talk about splitting into parts. I might run out of room, but hopefully we are going to draw 3 graphs, so kind of give yourself space as needed. So I'll stick with my colors, actually. Let's go ahead and do g of x, and let's think about f of x. And then we're going to cut off our areas at A and B. I don't know if I love this graph. It looks like these are symmetrical, but they are not. And let me change this. We'll do green area here. All right, great. So the first thing I want to figure out is this integral. So if I were to draw in representative rectangles Okay, so this area that's in yellow will be equal to the integral, starting at a for sure. Ooh, the thing is when I draw in these rectangles, this stays red minus blue the whole time until I get to this moment right here, and we'll call that C. So I need to figure out what C is, and we'll talk about how to get that in just a second. And then I do have g of x, red curve, minus blue curve, dx. So in thinking about that, to figure out that C value, I want to know where those two graphs would intersect, so I could set their equations equal to each other and solve them if I had the ability to do that. I also could graph on my calculator and use the second trace intersect feature to figure out that value of C. I would want to store that in my calculator so that I don't have any rounding issues, all that good stuff. So we're going to go from C to B. This time though, my representative rectangles still have a width of dx, but the height is dictated by the blue curve minus the red curve. All right, our last example then is going to be right minus left. So hopefully you have some room. I'm kind of running out of space a little bit. That's not what I meant to do. All right, focus. It's early in the morning. It's like 6:45 on a Friday, so give me a little credit. All right, so we're going to start with this weird sideways parabola thing happening, and we're going to go with a line. We'll call this guy G. I should have stuck with my colors. That was a terrible line. All right. This one, a little better. We'll call this one f of x. Stick with that blue. And I would like to find this lovely yellow area here. So if I think about representative rectangles, if I have this coordinate point where these are intersecting, and this coordinate point, if I were to draw in rectangles from top to bottom, I would end up with red minus blue, red minus blue, red minus blue, red minus blue until this moment. Then all of a sudden I go blue minus blue, blue minus blue, and I'd have to create two separate integrals. But if I'm a little bit more creative and I do my slicing this way, my representative rectangles then are just the bigger curve, which would be to the right on the x-axis, so f of x minus g of x, and then these right here represent infinitesimally small widths, but cutting along the y-axis. It's a change in y for your rectangle. So I'm going to set up just the integral for right now, and here I've got f of x, but you'll notice that this distance right here is not a function of x. It has to be a function of y. So I would have solved for x and gotten f of y minus g of y. All of that is being sliced perpendicular to the y-axis, so dy. And then instead of having a, we'll call this point a comma c, we'll call this one b comma d. Instead of looking from a to b, because that's just where the red was above the blue, right, perpendicular to the x-axis, I now want to look from the bottom to the top, is what I'm summing up those little green rectangles. So that's going to go from C until D. Again, our concept here every single time is a rectangle. So this rectangle, if I were to take it out and look at it as one purple rectangle, this has dy for the width. This then is a horizontal distance. It's an x value, which I would write then x equals a bunch of stuff that deals with y values, because x is what I'm looking for. All right, a couple more pictures. This is part of that explanation part. This video, I'm warning you right now, is going to get a little bit lengthy, but we're going to do one video with all the explanation stuff, and then you'll notice you have a bunch of sample questions. I'll take you through a second video to help you do those practice problems. Hopefully the explanation video will help you be successful on those practice problems. So we are going to now talk about volume. So volume is the summing up of area. If you remember thinking about geometry, if you put an infinite number of points next to each other, you get a line. Infinite number of lines, you get an area. Infinite number of areas, you're going to get volumes. So we are going to be summing up areas. We started by doing projected solids where those areas were different cross sections. So we needed to know things like circles, pi r squared, and semicircles, 1/2 pi r squared, and right triangles, which would be 1/2 base times height, and squares, which was side squared. Equilateral triangles was the square root of 3/4 side squared, etc. So what we were doing there is we would have some area that was trapped between two curves, like this, and that representative height or rectangle that I was drawing in the areas now became the side of, let's say, an equilateral triangle. And so this equilateral triangle is coming out of this video at you in three-dimensional space. It's being projected out of that flat area. So the next thing was we rotated these. We took an area and we rotated around an axis. The first way we started was rotating around some axis where the area was trapped right up against it. So let's say I have this blue curve and I had this, let me get a different color. I had this line, we'll call this y equals 2. Sure, why not? And I had this yellow area and I wanted to spin this around the line y equals 2. These cross sections are going to end up being disks that are perfectly butted up with that axis of rotation. Okay, so we have perfect circles, in which case you would be summing up pi r squared, and it would be your challenge to figure out, how do I write the distance of this radius? Well, that's going to be the blue curve. So pi, it's going to be the blue curve, we'll call it f, minus that green curve, which was 2. That's our distance, creating our radius squared, perpendicular to the x-axis, so dx. Then we upped our game a little bit, and we talked about what would happen if I took that same area and I rotated it around a line that was not right up against the area. So we'll call this our axis of rotation. We'll say y equals -3. Well, now when I go through and I think about these cross sections, I'm going to spin this blue one all the way around. So I could do an integral of pi with this big R squared. So this big R would go to my axis of rotation. That's going to be my blue curve f minus my axis of rotation, which is -3. Yes, I could clean that up, which I will in just a minute. Dx. So I would be finding this full thing as if this was all colored in yellow. But it's not. It has a big part of it taken out. So I need to then subtract off the integral pi of little r squared. So little r squared here is going to be from this green line down to my axis of rotation, those circles. So that's going to be 2, was my green line, minus that -3. All of these then would be going from your intersect points A to B, A to B. But our concept there was pi big R squared minus pi little r squared dx. The last thing then about rotating is we could go around the y-axis, which our setups are still the same. We're going to draw in our pictures and consider whether or not our area was butted up right against the axis of rotation, in which case you would just need pi little r squared, or if you were rotating around a line, rotating around a line where the area is not butted up against, then you would need the integral of pi big R squared minus pi little r squared, because you'd be finding big volume, this should be dy, big volume minus little volume. So the way to do that, when we're thinking about right minus left, this becomes then your radius for this yellow one. For the washers, you would need to find this distance as your big radius minus this distance as your little radius. Okay, so it helps to draw a picture. It helps to sketch it out just to get a good visual of what you're actually trying to find. So this is your first video with your crash course review. There will be a second recap 6 that takes you through all of those problems. It's up to you if you want to watch that one. I'm going to say this one should have been required. I'll pass that along to Mr. Lakin. The next one's out.